This video will be about rates of chemical reactions. First of all, let's talk about an example, and that will be nitrogen molecule into an O2 molecule, O2. Okay, the only way that you can get a chemical reaction between these two is if they actually collide together. Okay, and so that's what this process is depicting. The only way they can collide together is if they're traveling toward each other. Okay, if they're traveling in any other way, like where they miss each other, or if they're actually oriented even the wrong direction. Okay, so if we're going to form nitrogen monoxide, NO, we need to have them collide so that the N and O will be together during this collision so that the bond can form after the collision. All right, and so this is what's being shown here. So we have two molecules, bang, this is the energy of the collision, and then when they separate into two pieces, now they're two different pieces. Okay? So the energy has to be enough to break this bond, and you get some of the energy back from making this bond. But anyhow, so that's basically how reactions occur. So the more collisions you have, the more reactions you will have. Okay? Zero collisions, zero reaction. If you double the number of collisions, you'll have double the rate of reaction, usually speaking, although there are some exceptions to that. So the other factor is, of course, the energy of the collision. So if these things are just kind of puttering toward each other and just kind of go off, there's not enough energy to break the N-N bond in N2 or the O-O bond in O2, and so basically nothing happens. And so if we look at the air at room temperature, there's nitrogen molecules and there's oxygen molecules. The collisions are not making nitrogen monoxide because there's not enough energy in these collisions. However, in your car engine, which is very, very hot, thousands of degrees, there is enough energy for this reaction to occur. So what would come out of your engine is nitrogen monoxide, and that is not a good thing because nitrogen monoxide reacts to form nitrogen dioxide, which is brown, and you may actually see that in the air in Birmingham if the atmosphere is inverted, where basically the pollution stays in the city. So there's a device on your car called a catalytic converter, which actually runs the reverse reaction. It takes nitrogen monoxide at a lower temperature. Okay, now remember, at lower temperatures, collisions aren't so energetic, but it's still able to take NO and make it back into nitrogen and oxygen. Okay, so that's why catalytic converters are so important in an automobile. Lawnmowers don't have catalytic converters, so that's why in the summertime they tell you not to mow your lawn during the middle of the day in summer, because what happens, you get nitrogen monoxide, and then nitrogen monoxide reacts with other things in the air to produce ozone, and ozone is very hazardous. So there's a graph that shows the dependence on the collision. So this is the total energy of the molecules. Okay, so let's say the nitrogen and oxygen have a certain energy, all right? And then they collide. And so this is the complex. It's the activated complex, or the transition state. So this is the arrangement of the atoms in this collision that's going to lead to products, maybe. And so the products would be here. All right, so what this graph tells you is how much energy do you need to get from here to here, okay? So it's like, how much energy do you need to get from UAB to Homewood? Well, you have a mountain to go over. It's called Red Mountain. And so if you go up the full height of the mountain, well, you need a lot of energy to get up that hill. If you go through the Red Mountain Expressway, they've actually lowered the mountain, and so that's what a catalyst does. It actually makes it easier to get over the mountain because doesn't take as much energy. It lowers the energy requirement. Okay, so this is called, this energy requirement between the bottom and the highest point is called the activation energy. All right, so let's draw that. This difference here between that energy and the lowest energy is called the activation energy. All right, and so that's it for rates of reaction. Okay, so the rate of reaction depends on the number of collisions and also the energy of the collision. The energy has to be enough to get over this energy requirement in order to break the bonds. And then when you remake them, you get energy back. But the most important part is if you can't get to here, you can't get to here.